before we start, I'm going to recap a bit about effect of pH and pH thermostability. Last week, I'm going to share my screen. Okay. So we have this. Okay, so we have this two kind of pH study. One is optimum pH, another one is optimum pH stability. Okay, so for optimal pH, okay, if you look at this figure, we have B and D. For figure B, it is about we want to find which buffer or at which pH will give us the highest activity of the respective enzyme. Okay, so what we did basically in a lab manual, okay, so we have this range of pH from pH 4 until 11. The reason why we have different buffer, because each of the buffer, they will have the limits to reach that pH. For example, glycine NaO, it cannot drop until acidic because the nature of the pH is already alkaline. Okay, glycine alone is already alkaline. It's a basic characteristic. Okay, so for acetate, we cannot force it to become basic because acetate is acid, so we cannot change to basic. Okay, so for this case, what happened if you see the way we did the enzyme? Okay, we have the enzyme here, invertase. Okay, for our case, we have used invertase here. We have the substrate here. Okay, normally the substrate will be prepared using phosphate buffer base 7, which is here. Okay, but now since we are going to test at which pH will be the best pH for the invertase, so what we do, we will prepare the substrate here by putting the by dissolving this substrate, which is sucrose here in this buffer. Okay, so we have here and also the enzyme here. We prepare the enzyme, okay, and then the buffer to make up the total volume is this buffer. Okay, so we have here 0.5 ml of the invertase, and then we acid in the buff, and then we top up because the enzyme volume should be 3 ml. Okay, so why 2.5 ml? Okay, you look at the earlier part, you see here, we have put the enzyme 3 ml. Okay, or the 3 ml enzyme and then 3 ml substrate. Okay, if you go up still, we have 3 ml of enzyme, 3 ml of enzyme. Okay, effect of the enzyme amount, still we have 3 ml of enzyme. Okay, 0.5 plus 2.5, 1 plus 2, 1.5 plus 1.5. So that the total volume will be 3 ml. So for a start, because for the at the beginning we don't know which buffer, so we use with the phosphate buffer, which is a neutral buffer. I mean, I would say it is at pH7 because we don't want to introduce too much acidity or basic to the enzyme. So for now, we are investigating at which pH. So we have put the enzyme, we're going to put the enzyme at different pH. So basically, we have one overlap here, right? pH 7 here, phosphate buffer pH 7 is overlapping with the previous experiment. So yeah, that's the way how do we characterize. Whatever good things from previous one, we carry forward. Okay, so that we can characterize the next stage. I mean the next characteristic. Okay, so for now we have phosphate buffer page 7 with 0.5 mil. The total volume will be 3 mil, 2.5 and 0.5. And then we're going to assay with the substrate. Where this substrate, supposedly, we need to prepare the substrate using this respective buffer so that we can make sure everything is in the respective buffer. Okay, so now from this experiment, by the end of the day, we know that which one will be the highest, expression, I mean highest activity in which buffer. So we plot from 3 until 12, and then we got it. Yeah, for this case, you have only until 11. So, okay. So for this case, you have, thank you, Nani. So for this case, we don't have until 12, so we don't have to prepare until 12. But this one, you can see you plot the graph by using different series. I think it's different series, right? So your Excel, you can play around your Excel, you can get, okay, this square box, okay, graph represent sodium acetate. And then triangle is potassium phosphate. And then 3-CCl. And then asterisk with the glycinol. And then the last one, yeah, you have this buffer. Okay, still alkaline buffer. For this one, we end with the glycinol. Okay, so that's the thing. That's the idea. Okay. We now we know that the optimum buffer for this will be this point, pH 9, which is glycinol. Okay, for this one, let's check for the next slide. I think, yeah, okay, what buffer have they used this one? I think it is phosphate buffer. Okay, for this invertase, the optimum will be phosphate buffer. That's why phosphate buffer, no, this is not phosphate buffer. Yeah, for this one, I would say phosphate buffer pH 7. So, okay, so far we have used this one, so we are okay with this. So phosphate buffer pH 7 is the best, I mean the optimal pH for the invertase. Okay, so next we will investigate the pH stability. So for the pH stability, is similar to this. So what happened now? We have similar setup to this buffer range. Okay, we have this from pH 4 until pH 11. Okay, so we are going to incubate the enzyme. We're going to incubate the enzyme here with this acetate pH 4. Okay, we incubate this enzyme with this buffer. And then what happened next? Maybe after some time, which is maybe 15 minutes is enough. Okay, 15 minutes or half an hour, that's okay. 15 minutes at, maybe we want to incubate at room temperature. Okay, after incubating the enzyme and the acetate buffer here, what we will do the assay. So the assay, how do we do the assay? It's basically same like the one we did before. We get this mixture. So if you have here, for example, if you have invertase plus the buffer here, the total volume here, Okay, the total volume here will be 3 ml, right? Because you have 0.5 plus 2.5, we have 3 ml in here. So what happened next? Okay, from this 3 ml, okay, maybe you will take up 0.5 ml from this 3 ml. So this 0.5 ml basically a mixture of your enzyme just now with the acetate buffer here, mixture of this. So basically your enzyme now become diluted because you have mixed these two. Okay, so you have this 3 ml, incubate 15 minutes at room temperature. At the end of the day, you will take 0.5 ml out of 3 ml and then plus with the optimal buffer just now, which is phosphate buffer. Phosphate buffer pH 7. Okay, this is your optimal buffer where you have got the optimal buffer from the previous experiment. So 0.5 ml plus, for example, from here, 0.5 ml, 0.5 ml, add with the phosphate buffer, and then we do the incubation at 55 degree for 5 minutes, and then we terminate the enzyme activity. So same, phosphate buffer, enzyme plus phosphate buffer plus substrate. Don't forget about the substrate. So what substrate should we use? It will be sucrose. Yeah, substrate. Substrate. Okay, I got confused. Okay. Oops. How do we get that? What happened? Okay. Okay, I cannot get that thing back. Okay, never mind. So basically, we have got the enzyme just now. The assay, okay, 0.5 ml enzyme where you have incubated with this plus the phosphate buffer is 7, 2.5 ml, and then plus the substrate 3 ml, 3 ml substrate, and then after that you will assay at 55 degrees, just like, yeah, we will proceed, yeah, and then this one. Just proceed with the standard experiment procedure. Okay, so done. From this experiment, basically with that room temperature incubation for 15 minutes or half an hour. So what you can see, now you have got the optimal pH. I mean, the range of stability, pH stability now. So if you look at this D, you can see now the pH, the way we interpret this data is by looking at the range of pH where this enzyme can survive. Okay, for this case, if you want to talk about more than 60%, you can see that this enzyme stable from pH 6 to 11 with more than 60% activity. More than 60% activity. Okay, because this enzyme, when you incubate it with this respective buffer for certain time, the enzyme activity is still there. Okay, so do you think this activity, I mean, okay, the question here, let me just stop this. Okay, the question here, do you think the 100% activity of this point versus 100% of this, do you think unit per mil are the same or not? Okay, guys, what do you think about this 100%? 100% for optimal pH versus 100% of the pH stability. Do you think the unit per mil, when you do the assay, do you think the unit per mil will be the same or not? Maybe for this one, unit per mil is around 20 unit per mil. Then it make up 100% relative activity. Do you think for the pH stability, the 100% is similar to 20 unit per mil, or it is lesser, or what? What do you think? You can type in the text box, in the chatting box. Okay, lesser. Yeah, it may be different. It will not be the same, but it's for because we have performed the incubation just now, right? So once we expose our enzyme uh, at the temperature like room temperature, normally we preserve the enzyme at 4 degrees. Now, when we have incubated at room temperature for half an hour or something with the respective pH, definitely it will not be the same, or it should be lesser than the previous one. I mean the optimal pH, because optimal pH is exactly the minute you add the enzyme and the substrate, you immediately go for the reaction. But for this one, you put it outside for a while, so there must be some decrease, or I mean, yeah, in terms of the activity for the enzyme. Okay, so yeah, but the way we set up this experiment, I mean the enzyme characterization normally, we will standardize in terms of the milligram of protein. We will standardize in terms of the number of protein, the amount of protein we use. For example, for this experiment, for these two experiments, we want to use um, like 4 milligram of protein. If you want to use 4 milligram of protein, that means we need to calculate our protein exactly to be 4 milligram for each of these. Okay, we need to calculate our protein so that we can standardize. We can have 4 milligram for each tube, tube A, B until K. Okay, for example, if you cannot do experiment one shot, starting from tube A until tube K one shot. So what we do, we need to use similar amount of the protein so that we can have the answer. You cannot, today I use 2 mil. What is 2 mil? So very subjective. Or maybe I want to use 1 mil. So what is 1 mil? From 1 mil is very subjective. How much, I mean, it will be, oops, how do we get back to that? I cannot, bye-bye. Yeah, I cannot get it back. Okay, so if we have used 20 mil, 2 milligram, we want to make it 2 milligram for each tube. For today, you want to use 1 mil. 1 mil represent how many? I mean, for 1 mil is how many unit per mil? And then how many milligram per mil? So, but 1 mil is really subjective. So normally we will standardize using the milligram of protein, amount of protein we use for this experiment. Okay, so whenever you repeat for the next time, you will know, okay, I will need to use 4 milligram of protein, 2 milligram of protein. We cannot, yesterday I used 1 mil, today I want to use only 1 mil. Remember, you cannot simply use that because of you don't know every time. When you do the purification, you see you have the final yield, right? The final yield and everything. So you will have this batch, maybe the protein. I mean the protein amount, the protein, the milligram for me that you got is about 0.2 milligram per mil. So what happened to the second batch? Maybe you will get 1 milligram per mil. So if 1 milligram per mil, you took out 1 mil, that means you have taken 1 milligram. But for this, if you take out only 1 mil, it's considered you have taken 0.2 milligram. So these two, they are not standardized. Yeah, because this one is 0.2, this one is 0.1. How come? These two are not standardized because the milligram per mil, they are not the same. So we need to standardize in terms of the amount of protein when you do this kind of study. Okay? So okay, sorry. I have problem in the leg. Okay, so now we're done with this experiment. Any question for
Doktor, saya nak tanya.
hmm.
Kan tadi untuk kira pH stability tu kita mix dengan phosphate buffer kan doktor? Kenapa kita kena mix dengan phosphate buffer? Bukan nanti pH dia akan lari. Faham tak doktor?
Stability, for stability,
Mm-mm.
right? Okay.
Kan kita ambil daripada yang dah dilute-kan pH 4, lepas tu tambah lagi dengan phosphate buffer, right?
Hmm. Okay. The thing is, when you do the stability, we want this enzyme to react. For example, this enzyme react with this buffer, and final one you need to assay with the optimal buffer. Why optimal buffer? Not the respective buffer, just like the way we did this. This is because this buffer at this pH, okay, this pH has proven that this is the best pH for your enzyme. At this pH, your enzyme will give the best activity. Okay, if you assay, for example, you incubate 0.5 milligram, 0.5 ml of the enzyme plus phosphate buffer, acetate buffer pH 4, and then the residual activity you assay with the pH 4, so it will not be valid because you are still you know forcing the enzyme with this kind of environment where your enzyme just now it just want to be tested at this pH. Okay, you want the enzyme to be exposed to this respective pH, but at the end of the day you want to know how much residual activity left. What's left? Okay. For example, initially when you put the enzyme with the acetate buffer, the activity was 10 unit. But after exposing these two, incubating this enzyme and the pH for half an hour at room temperature, the residual activity is just 2 unit. This residual activity need to be assayed using the optimal buffer. We cannot use the similar buffer. It will end up having 0. Okay, because this residual activity only 2 unit. Okay, so we need to to give the best condition to the enzyme because we want to know what is left. Okay, Anani? Anani, you are the one who asked the question, right?
Amalina, Doktor.
Amalina, sorry, Amalina. Okay.
Thank you, Doktor.
Okay. So, so now we move for the next step, which is effect of temperature. It's a bit similar to the pH. Okay, let me just scroll down. Okay. So for the effect of temperature here, what we can see, we have, we want to know now what is the optimum temperature for the enzyme that we want to study. Okay, we can set whatever temperature we want. Okay, so for now, for invertase, for our case, we have invertase here. We want to see what is the activity at what time. I mean, at which temperature your invertase will give the best activity because we don't know now which one. So what we did, test tube A, B, C, D, E. You put the enzyme, 3 ml of the enzyme in tube A and incubate inside the chiller. So for this one, you need to find chiller, 4 degree. Okay, we have chiller. Okay, and then this 25. 25 normally we want to consider this at the room temperature. But to make it best, we should find an incubator with 25 so that we know exactly, we record exactly the temperature for it, not just like room temperature very subjective. Room temperature in here, room temperature in different place, room temperature during summer, room temperature during winter. So it will give you different kind of temperature. So for this case, we will need to find 25 degree incubator so that we can have this room temperature environment. Okay, and then for 40, we can have the water bath. Okay, we can have the water bath. Okay, so this for 40, we can have the water bath. Okay, so same goes for the 55 degree. We can have water bath. Okay, so this one we can go for water bath. 90 degree can also go for the water bath. So we have this 4 degree, 25, 40, 55, and 90. So we have set similar enzyme amount, and then the substrate we use sucrose. Okay, because we have got the answer, sucrose is the best substrate, so we maintain the sucrose. Okay, so now we are going to investigate at which temperature will give you the highest activity. This is what optimum temperature is all about. We want to find the highest activity, okay, for the enzyme at which temperature. So if you look at this paper, we can see here they have selected temperature 40 until 80 degree. Okay, so for us we have 4, we can put 4, 25, 40, 55, and 90. Okay, so for our case, the x-axis should be the temperature. Okay, y-axis still the relative activity. Okay, so we want to find at which point, at which temperature will give you the highest. Okay, for this study, the answer will be 55 degree. So the graph will be like this. Okay, then towards 90, it go down. At least the graph, we have the bell shape. So if you check on the A, B, and D graph, you can see all of the graph is showing, okay, all of them are showing the bell shape, from lower going gradually increase and then gradually decrease. Same goes here. From going down and then you gradually increase and gradually decrease. Same here, increase, decrease. So that you will have the optimal point. You will have this optimal point. So for this case, our optimal point will be 55 degrees for this experiment. So that you know, okay, for invertase from Saccharomyces cerevisiae, the optimal temperature is at 55 degrees. So what if your result you got like um, from 4 degree, you get like this? So if you have like this, that means your optimal temperature was at 40 degree at this point. So you will find it. Where is your optimal temperature? For this case, we have done the experiment before. The optimal temperature was at 55 degrees. That's why we choose 55 degrees. Okay, for example, let's say from this optimal temperature, what you got, the answer gave you like 40. Okay, suddenly you got the answer, the highest one was at 40. What do you think about the previous experiment? You have performed everything at 55. What do you think? Okay, the different, okay, for example here, you need to add invertase and substrate in your mixture, and then instead of 55 degree, you incubated at 4, 25, 40, 55, or 90. But the result shows that the highest activity was achieved at 40 degree. The question here, you have done effect of pH just now. You have done the pH, optimal and stability. You have done the substrate specificity. You have done the substrate concentration. You have done the enzyme concentration. All of them you have used 55 degree, right? Yeah, all of them here you have used 55 degree. Oops. For the incubation for 5 minutes. What do you think? The answer when you do the optimal temperature, it shows 40 degree. So what do you think about the previous experiment? Should you repeat the experiment or never mind, just forget about it, proceed with the next study? Just carry forward whatever good things from the previous one, bring it forward. So what do you think? Okay, Hanan will say proceed. Others? Okay, Toba, you don't have to repeat. Okay, just proceed. Okay, Irfan says proceed. Yeah, you need to proceed. Yeah, we need to proceed. We don't have much time to repeat whatever behind. Whatever, because previous one was done because of we don't know. Now we know the answer. We proceed with the optimal one. Okay. So, okay. So we are done with the optimal temperature. Do you have any question for optimal temperature? Or actually proceed with the thermostability? Any question for the optimal temperature? No? Okay. So, okay, so now I need to pick up the phone from SCS. I need to make Okay, so it's about to end. How long do we have? Or else we wait for the second session. How long? Do you have 2 minutes? Iwi? 2 minutes, do you have it?
Yeah. Left 2 minutes for the meeting.
1 minute.
Yeah. Probably.
Okay, yeah, we will make it quick. Okay, so for this one, if you compare yours, compared to this, okay, okay, why this study use 40 to 80? Why not just like yours, 420, 40, 55, and 90? Why not? Why it is like this? Because this study, the reason why we set from 40 to 80, because the enzyme that we are working on is a thermostable enzyme. It is a thermostable enzyme where this enzyme can tolerate thermostable enzyme, where this enzyme uh, can be active. Okay, they are active at high temperature. Okay, they can yeah, it is not easily denatured or something. It is the reaction time, the reaction temperature will be at higher temperature. That's why we do not test at 4 degrees. Why do we need to set 4 degrees? Because the nature of the enzyme that we're working on now is at thermostable. It is a thermostable enzyme. Okay, if you're working with saccharophilic enzyme, the saccharophilic enzyme, the saccharophilic enzyme is enzyme prefer cold temperature. So you don't want to test until at this temperature. You should have like 0 degree or 1 degree, 1 degree until 20. You want to consider this is under